Hi, my name is Ada Lund, Senior Software Engineer at Datavant. Today's talk is going to cover a lot of what we've talked about the past days. That is to say, cloud, infrastructure tooling, infrastructure management, monitoring, metrics, etc., but from the perspective of test, and more specifically, performance testing tools and frameworks, which are a critical part of a DevOps engineer's toolkit. Performance testing frameworks allow DevOps engineers to write tests that stress the systems that we build and maintain and help us gain insight into how those systems handle traffic at varying degrees of scale. So for me, this starts back in 2020. When I came down here to Austin to start at Zebra, I was almost immediately tasked with implementing performance testing for our DevOps and infrastructure team. We had a variety of needs for performance testing. First of which was we wanted to be able to test how changes to our underlying infrastructure affected the service as a whole. This means things like updating our autoscaling config in Kubernetes or implementing Linkerd proxies. In addition to that, we needed the performance testing to be able to emulate realistic usage scenarios at varying degrees of scale during disaster recovery scenarios so we could truly understand how service failures impacted the application as a whole. And finally, the much more standard use case, which is we really just needed a beat on how our systems handled varying degrees of traffic. This resulted in a pretty interesting set of requirements, though. The first of which is the realistic usage scenarios. The tool that we chose had to be able to address these. In addition to that, we used Datadog primarily for our monitoring and metrics and gathering, etc. And the performance testing results needed to be able to publish to Datadog. Finally, the tests themselves had to be able to run in our CI/CD and eventually our Kubernetes environment. That way, engineers wouldn't have to continually reach out to yours truly to schedule and run tests. Now, for those of you that know, this means that the pain started almost immediately. First off, we found that for the performance testing frameworks that allowed us to author much more kind of realistic user scenarios to emulate that behavior, they were much more resource intensive and did not play nicely with our CI/CD and Kubernetes. In particular, it came down to running out of memory, consuming too much CPU. Kubernetes and CI/CD environments are much more resource restricted than what these softwares are used to being run on. In addition to that, we found that getting results out to Datadog for all but a couple of frameworks was an extremely arduous, if not impossible process. And even for the frameworks that allowed it, it often meant compiling and integrating custom third-party extensions or writing the extensions and integrations ourselves. And then finally, the developer experience all around was just rough. Poor documentation, clunky CLI. It felt like these tools were written in the last decade. And sure enough, many of them started back in the double S and hadn't really changed or advanced since then. This lets the question why, and well, I think I might have an answer for that. The answer is the test Ouroboros. That's what's keeping us stuck back in around 2005 when the last Fantastic Four movie was released. You see, test tooling is often treated as a cost center, and not without some degree of justification. You see, test tooling is often very rough on developer experience, and it takes a lot of time and effort and money to get it to address the actual scenarios that you need it to address. For that reason, it being a cost center, we don't tend to invest a lot of time, effort, money, etc. in improving the developer experience, performance, or features of these tools. That results in the DX performance features stagnating, which over time means that there's only further amplification of the inertia, of the friction, of the pain that developers experience when implementing these tools to address their needs. And thus the cycle repeats. For me, this comes down to two sides, which is one, compute has changed a lot. When these tools were written, for large part, back in the double O's, we were mostly running on, say, bare metal servers, clusters of VMs. That's not the case anymore. Modern compute infrastructure is complex and sophisticated, using a variety of databases. There's serverless. Kubernetes is now the dominant way of running distributed services. Then on top of that, back when these services were written, putting out results to, say, CSV, XML, JSON, static file format was perfectly fine because the compute that you ran on was not ephemeral. You could easily go in, grab the files, get them out, a quick script to aggregate them, and you were good to go. Nowadays, we need these metrics up with our modern dashboards, say Grafana, Datadog, etc., or even in databases where they can be further queried and analyzed. All these frameworks don't account for that sort of usage, and it makes maximizing the context of their results exceptionally difficult. And finally, more so than ever before, our users are global. However, these testing frameworks don't allow us to realistically emulate that global usage very easily, at least in many cases, not without paying a pretty penny for enterprise subscriptions. This all comes down to the other side of the coin, which is that the world itself has changed a lot and is much more unpredictable. Even your average web application now demands more scale. It has more moving parts. And things like virality, sudden explosions, popularity just weren't really a thing when a lot of these performance testing frameworks were written. So you had more time to test individual scenarios, write them all out. It's not the case anymore. We need frameworks that let us quickly and rapidly test, prototype, adapt, and adjust to changing scenarios, whether infrastructure changes or user usage scenarios. That and applications are more sophisticated than ever. It's not just HTTP and UDP. We have HTTP2, HTTP3, GraphQL, and we also need to test our UI services, which are often just as resource intensive as the backend ones. We need frameworks that then are also able to capitalize upon their own testing results. You see, performance testing frameworks generate a lot of data. However, none of these frameworks really tend to use that to their advantage to, say, do things like minimize configuration over subsequent test runs. We just deserve better. Executing distributed shouldn't be optional, first and foremost. Given that most computing is in some way, shape, or form distributed, performance testing frameworks need to update and reflect that reality. Going along with that, running tests, whether local, CI/CD, or distributed, should not involve massive configuration and/or test code changes. We shouldn't have to waste time in that regard getting results where we need them as well. Real-time testing and just realism in scenarios should also be a non-negotiable. We should be able to reflect what our users are doing in our performance test codes as much as any other type of test. And for that reason, frameworks just need to be more user-friendly. Ready for the fun part? I'm a believer that if you have a set of problems, it's a set of opportunities, cheesy how that sounds, and that if you're going to complain about something, you better have a solution. What we're going to do here is we're going to build a new class of tooling that embraces the best parts of performance testing frameworks while solving these problems. Let's get started with some requirements. First off, realistic usage scenario simulation. In my mind, this means that at the core level, the framework should allow us to author tests like integration tests, but execute them at the scale and with the speed of performance testing frameworks. In addition to that, it means that it should embrace things like, say, data science or chaos testing methodologies and or algorithms, features, etc., to automate things like configuration and help us better automate the testing of changes to our systems, whether at infrastructure or application level. Again, hammering on this one, we need modern integrations. Spitting out files for results anymore or just pointing them out to the CLI, although useful, is just not enough. We need to be able to submit results to where they're needed and not have to use things like clunky extensions or writing our own, heaven forbid, to get results where we need so we can maximize the context that these tests deliver. Next, this is non-negotiable, and I hope you'll agree with me. Good developer experience, and in my view, this starts with a quality CLI. No antiquated, arbitrary, opaque arguments, good, solid, documented, good help, features, same defaults, the lot. On top of that, a good quality API for us to write tests with that is informative, descriptive, but not too complex or sophisticated. And then finally, distributed is not an option. As I said before, we're not running on bare metal or even clusters of VMs anymore. Performance testing frameworks should allow us to run whether CI/CD, distributed like Kubernetes, or even serverless environments. Let's start with the real scenarios. So what you see here is some example code from the framework that I'm building. In this case, also not so very hypothetical anymore, but we're going to still say that this is hypothetical. And one of the things that I often encounter when working with existing performance testing frameworks is that, again, it's very difficult to simulate realistic usage when you are writing tests as, say, a set of static CLI args, or as data, say like JSON, XML, etc., or as a configuration language like YAML. For that reason, we need this framework to involve a real programming language, whether, as in this case, Python, Golang, you name it. What this lets us do is it lets us parameterize the tests, meaning that a single test can deliver on a number of different scenarios. It also means that we can do things like integrate tooling or other libraries from within that language's environment to help us simulate the usage. while minimizing the complexity of the framework itself, as well as the developer writing these tests having to write these sorts of tools to work within the framework itself from scratch. Another common thread with existing performance testing frameworks is that if they let you write quote unquote realistic user scenarios, they only let you execute steps either randomly or in sequential order. This is not enough. The reality is that users work in workflows, particularly if you want to test at all layers of the stack. You see, a user might click a button, and that's one interaction. But behind the scenes, that might launch off any number of concurrent jobs, requests, etc. In order to capture that behavior, we need to write tests as workflows. And to my mind, in particular, directed acyclic graphs. Pairing that with the ability to support multiple protocols within the same test. So say I use the playwright protocol to simulate the user clicking the button for the test, but then underneath that, I'm also within the context of the same test, able to emulate the HTTP requests, HTTP2 requests, gRPC calls, whatever have you, to test the entire stack from top to bottom for the workflow. The effect of this is that we now have the ability to simulate user interactions at every level of the stack. A single interface, minimal duplicate tests because of the parameterization, and then on top of that, just less clutter, less chaos. Speaking of which, let's embrace some data science and chaos testing. Now, I know everybody's doing an AI talk nowadays, but this actually has a point. You see, performance testing frameworks generate a lot of data in their execution, particularly data that pertains to your environment. And this is not just valuable to you. That can be valuable to the framework itself. Now, taking aside from that, one of the things I first want to call out is that when we deploy changes to any environment, whether infrastructure or application, we often do this through a number of environments. So for example, development, staging, production, etc. A/B testing makes automatic sense here. So why not include it? In this way, if I make changes to my infrastructure in, say, development, I can have a single performance test, use A/B testing to divide concurrency and traffic between the different environments and actually help me calculate what the real impact of those changes are without having to repeatedly run tests targeting the different environments. Then we can use, again, the data from those tests to automate the configuration and help make sure that you don't have to go back in and manually adjust a bunch of parameters every time you make a slight change. The framework can pick up on it automatically. And now to the storing of results. I think I've hammered on this one enough. Spitting files out is not ideal for performance tests anymore. But the reality is that we store metrics, results, data, etc. in a variety of different places. And we need to be able to reflect that and control that from the test code itself. This means good, solid reporting options as a part of the tool, as a part of the framework. And what this also means is that we're reducing a lot of the work of developers, particularly DevOps engineers, in getting the results where they need to make decisions quickly. We're reducing the friction is what it really is. We are reducing the amount of time it takes for developers to understand what their systems are doing at scale. And then, non-negotiable, quality DX, whether local or distributed. What does that mean? Well, for me, quality DX means something as simple as a quality CLI with good, helpful args, sane defaults, etc., to making sure that the tests do not require massive configuration changes to run across different environments. One framework, current performance framework, that does get this correct, in my opinion, is something like Case 6, that lets you from one CLI run in, say, cloud mode on Case 6's services, or local, or within your own Kubernetes cluster, etc., etc. This is something that our tooling should embrace. In addition to that, our tooling should embrace things like, say, code generation for generating stubbed out tests so developers can get up and running as quickly as possible with some boilerplate. Things like being able to submit test code directly from their laptop via RPC to a running cluster instance and submit as jobs their tests, thus meaning that they don't have to wait on clunky, convoluted CI/CD pipelines to pick up and run the tests. They can just run it right there and get that immediate, tight feedback loop. We're going to call this a simulation framework. So let's formalize the definitions then. Simulation frameworks allow developers to write tests that look and act as integration tests, emulating realistic user workflow while executing at the speed and concurrency of performance testing frameworks. Simulation frameworks should utilize data science approaches, apply statistics, etc., to automate configuration changes and also help developers write tests that better help them understand how their changes impact the whole systems. On top of that, simulation frameworks should be modern cloud-native frameworks. They should support modern computing environments, whether VMs, bare metal, Kubernetes, serverless, etc. Simulation frameworks place developer experience first. Much like, say, modern webdev frameworks, they make using them a joy, and they make the point of quick feedback loops, quick feedback cycles, good informative experience the most important thing. They maximize the developer's happiness this way. And then finally, simulation frameworks work and play nice with other things. That is to say, they have plentiful integrations with common reporting services, databases, etc., common protocols, you name it. Okay, we've now reached the end here. This is it. I want to give a final note. The important thing to come away with today is the concepts: simulation framework, realistic usage scenarios, using modern computing techniques from data science and chaos testing to really maximize context delivery. Sure, you've seen some code, and that is the framework that I'm building. It's called Hedra. It's up there on GitHub. You can find it. I'll link it down in the README notes. But the thing that I want you to come away with today is that we can do better for ourselves. As DevOps engineers, we live and die by the insight that we can glean from our applications, where monitoring, metrics, observability, etc. Simulation frameworks, I think, are a critical asset in helping synthesize that insight, so that way we can understand how our systems respond before it becomes too late. I hope you've enjoyed this talk, and thank you.